Where the Pacific Ocean violently collides with the San Francisco Bay, a treacherous 300-foot deep chasm of freezing, swirling water once mocked human ambition. Winds howling at 60 miles per hour and blinding coastal fog made the very concept of a crossing seem like a maritime suicide mission. Yet spanning this violent strait became one of the most audacious technological imperatives of the early 20th century. The Golden Gate Bridge was not merely conceived as a transit corridor, but as a direct challenge to the supremacy of nature. Chief Engineer Joseph Strauss stared into that abyss during the brutal economic nadir of the Great Depression and envisioned a suspension bridge of unprecedented scale. Pushing structural engineering to its absolute limits, his design required towers soaring 746 feet above the water, taller than any building in the city at the time. To anchor such a colossal megastructure, teams had to conquer the ocean floor itself. The 1930s construction effort demanded not just raw steel, but a radical reinvention of how humans operated in hostile marine environments. The foundation of the South Tower required men to work inside massive underwater caissons, effectively plunging them into a turbulent, blind void. Divers descended into pitch-black, freezing currents, placing explosive charges by touch alone while fighting tides that threatened to sweep them out to sea. It was a perilous, death-defying dance with the elements, where a single miscalculation meant being crushed or drowned. This subterranean battlefield tested the absolute boundaries of human endurance and the reliability of early deep-water diving apparatuses. Historically, the grim arithmetic of such monumental endeavors dictated that for every $1 million spent, one worker would die. Strauss, however, refused to accept this blood sacrifice, fundamentally altering the ethical landscape of industrial labor. He mandated rigorous safety protocols, including the mandatory use of hard hats, glare-reducing goggles, and specialized wind-blocking creams. More profoundly, he invested $130,000 in a revolutionary concept that would completely redefine the value of a human life on a construction site. Suspended beneath the rising roadway, a massive web of manila rope became the most vital engineering innovation of the entire project. These sprawling safety nets caught falling steel, dropped tools, and, most importantly, human beings who slipped from the dizzying heights. 19 men plummeted into that webbing, surviving falls that would have otherwise been fatal, and subsequently formed the exclusive Halfway to Hell Club. This physical safety layer instantly catalyzed a psychological transformation among the ironworkers. Relieved of the paralyzing terror of a lethal plunge, the crews moved with unprecedented agility and speed. The unseen cost of this newfound confidence, however, was a subtle recalibration of risk tolerance. Workers began taking bolder chances, walking narrow beams in high winds with a swagger born of the safety net's psychological cushion. This phenomenon, where technological safeguards inadvertently encourage riskier human behavior, remains a profound paradox in modern automation and cybernetics. Beyond the immediate peril of gravity, the structure faced the existential threat of the Earth itself. Situated perilously close to the San Andreas Fault, the bridge required a pioneering approach to seismic design. Instead of rigid defiance, the engineers built in calculated flexibility, allowing the massive span to sway up to 27 feet laterally to absorb the kinetic fury of high winds and earthquakes. This principle of dynamic yielding over brittle resistance became a cornerstone of modern structural resilience. The echoes of that Depression-era ingenuity still resonate through every modern megaproject. The successful integration of Strauss's worker protections and the dynamic seismic flexibility prove that massive technological leaps did not require a corresponding toll in human lives. That suspension span over the bay ceased to be just a local triumph, transforming into a global template for harmonizing extreme scale with human vulnerability. The lessons from that industrial era never faded, setting a new baseline for ethical engineering. Today, those same principles of resilience and safety dictate the construction of skyscrapers, deep-sea oil rigs, and even orbital habitats. Yet the Golden Gate Bridge itself remains locked in an endless, automated battle against its own environment. Advanced sensors now monitor its micro-movements, while continuous maintenance crews fight the relentless, corrosive bite of the salt air. As sea levels rise and climatic extremes intensify, the structure's original tolerances are being tested by a future its creators could only imagine. Ultimately, this iconic orange span is much more than a functional transit route or a static piece of history. It stands as a profound testament to a moment when humanity chose to prioritize the lives of its builders as highly as the grandeur of its vision. By weaving together radical engineering, environmental defiance, and an uncompromising commitment to human safety, the bridge bridges the gap between our fragile mortal limits and our boundless capacity to reshape the world.